Welcome to another edition of Inside the Challenge, and I have returning today Brooke Guzar from Blackwell Engineers. Brooke, thank you for joining. I was told to just like let it rip, so we're just going to let it rip. In the kudos to the bear. Thank you.
I have not seen the new season, so
Fantastic. All right, well, we're not here to talk about the bear, but we're here to talk about a subject that Brooke hasn't even told me yet, so I'm excited. She's
exactly.
going to share the screen. Here we go.
So I'm going to show you a project that was really challenging for me. It was one of my last ones I did before becoming CEO of Blackwell, and it's out on the East Coast. So I'm going to take you on a quick little tour here. Just let me get this sorted out. There we go. So we're here in Toronto, where our main office is, and if we zoom all the way out to my favorite place in the world, Nova Scotia, down into here where we can see Halifax. And then out on this beautiful little peninsula, the Aspetogan Peninsula, right over here, overlooking the ocean in a beautiful, secluded spot that is an incredible site to build a very fancy house.
Okay, here we
And
go.
that fancy house looks like this. This is called Rockbound. The architect was Omar Gandhi. It was a blast to work with them. They're really creative and collaborative, and we just have so much fun. And they're really challenging. There's a lot of elements in here to make this structure. And one of the main drivers of the difficulty of a project like this, where it's situated, is the wind. It's windy as heck out there. There are hurricanes, there's all sorts of stuff. And so while a structure like this is easy enough to manage from a gravity point of view, it's quite difficult laterally. And as structural engineers, that's sort of the most important part of our work is managing those gravity loads and figuring out how do we support those lateral loads. And so I wanted to share a little bit about our design process.
Okay.
Um, this would be our structural drawings here. The foundations on this project were really difficult too. I'm not going to focus on those, but once we were out of the ground and we had this good concrete base that was anchored down into rock, we were able to build this superstructure. And when you take a look at the plans for this building, there's a number of walls and a number of open spaces. And so we have to find areas where we can carry those gravity forces down to the rock, but then bury strategic lateral elements within these walls to make it sort of magical and open and inviting, but super duper strong as well to deal with these lateral forces. And so what we came up with is taking our structural plan and then finding these areas of lateral support that we can use our different tools between steel brace frames, concrete shear walls, wood shear walls, and whatever sort of blend of these systems will help us manage the extreme winds that something like this is going to experience. And so it's kind of science of looking at where your openings are and where you can deal with these big forces that are coming into this building. Um, and so here's where we landed. These blue highlights are the lateral systems in the uppy downy direction, and the other ones are the lefty righty paths. And you need multiple elements to help support these. And so as we zoom in here, we can see this is a shear wall. Its force that it's receiving is 10.6 kilonewtons. We've got a really stiff brace frame here in the north-south direction, 42 kilonewtons per meter. That's a pretty high force for something that is this small. And managing that all the way through the structure up to the upper levels and down to the lower ones, it just needs a lot of thought and analysis. So here's our structural plans, and it sort of shows where those elements live. We've got one here, you got your brace frame here, and sort of translating that now, all the math we've done behind the scenes into the drawings, and then identifying how we are going to tie all these forces together and get them into those lateral elements. So this is a elevation of a brace frame. This is really complicated. We've got a lot of wind that's gonna blow on the structure, and it hits these walls and it transfers up here and then into this diaphragm, and then we have to get it down from the diaphragm through these trusses down into this steel and then down into this brace frame. back down and out and down here. So this is called the complete lateral load path. And sometimes it's really easy and clear, and sometimes it's really complicated and nuanced. This would be, I don't know, a mediocre complicated one. At least we have these frames that are stacking
Mm.
with each other, and so that's really helpful. But sometimes they aren't stacking, and you need to drag these forces around. Here's a really complicated top of two shear walls that are working together. They're wood shear walls, and we have forces coming in from the side here, pretty hefty ones, either direction, and we are carrying them through, dragging them through this wood diaphragm here, and then down into this top plate of the shear wall, and then down and out through this shear wall, the sheathing on it. And then we're transferring some of those forces through this strap that then brings in this shear wall and works together. So it's pretty complicated. When you hear engineers talk about the lateral load path, it's something that we're often thinking about and that we often lose sleep on as we're trying to work through the design. And when we do come come to our sort of scheme about what it's really going to look like, then we have to put all the numbers to everything and do an analysis on that. And we use several different pieces of software from hand calculations all the way to really detailed um, software that you can kind of run. You build a bunch of sticks and nodes to put them together, and they end up. We apply the forces that we expect these elements to see, and then we push on them. We press go, and we see what happens to them. So here's sort of these isolated steel elements throughout this building that were really strategic in helping manage those lateral forces where a wood wall just couldn't handle those large forces. This brace frame over here is the one that had that 42 kilonewtons of force on it. Um, Over here, this small one, which kind of was a very critical one.
Yeah.
And then we had this big expanse of windows over here. So we had this really long moment frame in this direction, and then another brace frame that was working reasonably hard. And so you can sort of see that in this model here. And as we apply our wind loads and our snow loads and our dead loads, uh, and make sure that the system isn't going to deflect too much and that it isn't going to collapse from the gravity loads, and how these all things interact. And the next tough piece is bringing those forces down into the anchorage,
Yeah.
down into the foundations, out into the soil, out into the rock, whatever it is, for a complete lateral load path.
Amazing.
It's
I,
a crazy
I
building.
I'm curious because I don't know the math on this. What does the 42 equate to in terms of um like kilometers per hour or miles per hour? Or is it would it equate to something of that type of equivalence?
Yes, we have a pressure applied, and it's all statistics. And so let me just dig into some folders here and find some uh loading. Right from beams, archive shear walls, seismic loads.
Sorry for putting you on the spot. You could just say, I don't know.
I mean, this one is just really strong because it's also on a hill, so we have to
Yeah,
speed it up too, which
right.
is pretty interesting. I guess I might be in loading in here. Lateral design, shear wall design, wood shear wall deflection. Yeah, I can't quite find it quickly enough.
That's
It's been a
okay.
long time since
You
I
want to
was
hear
in
some?
here.
So stop sharing for a sec. It's fine.
Yeah, let's just talk about it.
Yeah. You said 42, right? Uh,
42 kilonewtons in that brace frame alone, which is a collection of all sorts of wind loads from that total path.
kilo, to kilometers. I'm just curious. I'm going to search.
Seismic loading. Oh, I might have found our spreadsheet.
And I only asked this question because I'm curious based on where you're suggesting this is. I'm assuming like you have to factor in like the hurricanes that can come through this area potentially, right?
And so our buildings are subjected to these forces that are we've studied over time, and the highest probable wind speed that this structure might experience in a certain period of time. So it's a lot of statistics,
Right.
and those numbers are provided for in the Ontario Building Code or the National Building Code or whatever code you're working for.
Yeah.
And it's all based on history and crunching some numbers, applying factors that bump them up for security, for safety factor, and making sure that we're not necessarily perfectly right, but we know we're not wrong.
Right. That's fair.
Yeah,
I
it's
just
fun stuff.
I've run this through GPT for the purposes of trying to see if I can get a quick answer on it, and it's still building the calculation. So, uh,
Yeah.
for, for those of you still with us as when this is released, bear with me. While Brooke's looking on her side, I'm trying to see if okay. So
So our worst one, because of the speed up factor, we end up with 1.04 kPa, kilonewtons per meter squared. Uh, and so it's a pretty strong force. And yeah, it really adds up when you have large areas that catch that wind and we
right.
need to manage it through the system. So
So it's saying here, yeah, at 8.1 meters squared. If the length was 3 feet and it was 2.7 meters high, the wind speed would be 331 kilometers an hour.
that's too much. We've got the 1.6 kPa would
Point 6.
be, yeah,
Okay.
1.6. Try that. Slam it back through ChatGPT.
1.6 kPa. Let's.
Hmm.
I want to learn this. So in like some short form.
And yeah, that's our 1 in 50 year wind speed is sort of the root of this. And then we add on geometrical factors,
Yeah.
if it's on an escarpment, if it's on a hill.
Right.
And so that 1.61 gets multiplied by 1.45 in this case. And then there are considerations for things like a corner of a building. A corner, as that wind hits it and goes around that corner, creates stronger forces concentrated there that dissipate down the length of a building. So there's a lot of moving pieces. And when you hear an engineer talking about that lateral load path, uh, it's
Okay.
deeply important.
Got it. It says a wind pressure of 1.6 kPa corresponds to about 184 kilometers per hour wind speed.
Yeah, which is very, very high, right? Like
Yeah.
I've lived in
Yeah.
Nova Scotia. Some of the wind speeds there would, yeah, maybe 120, 140 in
Yeah.
hurricane times. So there's that extra level of
Yeah. I mean,
safety
you
that
have
we
to, right? You'd
consider.
have to.
Yeah.
Yeah.
So it's
Okay.
super fun. So that's my little
Very,
tour through.
very interesting. Because to me, this is something that I can connect with. When you see the wind warnings online, is my roof going to rip off?
Yeah, it's a
Right.
real thing.
It's a
So,
real thing. Yeah, you see it in the news when hurricanes and tornadoes come through. Brooke,
yeah.
I apologize for digressing on this subject a little bit, but I just find that element to be one of the more interesting things.
Well, it's
So
fascinating, right? It's like it's an invisible force. You can't
yeah,
see it, but you can feel it, and you know that it needs to be accounted for in our
yes,
designs, and our understanding of it over time allows us to make big skyscrapers and huge buildings, and even manage these all the way down to a house that is architecturally interesting. And
yeah,
yeah, it's really fun. I love being
appreciate
an
it,
engineer.
Brooke. Thank you for bearing with me.
No problem. Thank you so much.